Question to Cosmo. Which of the developments in the past few months that you've presented do you think obviate the gaps that the other two presenters have talked about?
I don't think the gaps that they've mentioned have already been solved. I just think that the selection of work that I presented begins to address those issues. And the ones that I presented were the ones that I thought were the most relevant. There's obviously additional work that has been done.
You don't have to get up and run.
Okay. Up towards that.
Hey, how important do you think online learning is for AGI, and is there any hope of deep neural networks at some point moving towards online learning mechanisms, as opposed to offline? Do I need to explain that?
You mean essentially single shot table learning?
No, where you go off and you gather a whole bunch of data, you go sit back and crunch away. That's all what I mean by offline learning.
Like
As opposed
batch
to
mode
learning.
instead of incremental.
Yeah, right.
So in this mode, is the microphone on? Do I need to hold this down in order to talk? Does it make any difference?
Turn screen.
Turn screen.
It's green.
It is on.
Okay. Okay. So personally, this is about filling the gap. I think that online mode makes a lot of sense. My background is colored by the fact that I grew up as a roboticist, and a robot wandering around gathering information doesn't get the luxury of collecting, gigabytes and then processing on it. But it's most efficient if it can use it as it goes. So all of my work personally focuses on that. That's my gut instinct. I don't know of any fundamental result that says that has to be the way.
I will say, even though I'm doing reasoning, I will say online learning is necessary for AGI.
All right. Stand up and talk.
Yeah, sure. So in my own thinking about how to leverage what's good in recent deep learning algorithms and overcome what I see as the shortcomings within our OpenCog project, I've, with my colleagues, sort of tossed around two different alternatives, and I'm curious for feedback on the strengths and weaknesses of these two alternative approaches. And this is from the standpoint of having a cognitive architecture that philosophically is sort of deep learning focused. If you look in terms of Stellan Olson's high level concept of what is deep learning, I mean hierarchical pattern recognition, but it's not a deep neural network in the sense of convolutional neural nets and stacked autoencoders and so on. So approach A is take something resembling a current deep neural network and run it as part of an integrated architecture together with something that is not a deep neural network, and then put links between them so that your other thing can provide sort of cognitive modulation to the deep neural network, as well as reading perhaps internal states as well as outputs from that deep neural network. Approach B is to construct within your other non-deep neural network AI system, construct something which in some ways resembles a deep neural network, perhaps having a similar topology that reflects the structure of certain types of data that you have to deal with, because even if you're building a logic system, perhaps a part of your logic system dealing with visual data wants to have something like layers of two-dimensional arrays, since that's sort of what the visual data has, and then sort of reconstructing that topology within your non-neural network system, but then doing the learning and adaptation using algorithms that are completely different than whatever you have in a deep neural network. So learning something from the processing flow, perhaps, but not using those algorithms at all. So these are two different ways that whatever success of deep neural networks teaches us could be infused into a non-deep neural net type algorithm. They each have strengths and weaknesses, and we started with one of those ways and are gradually kind of shifting toward the other one as our work progresses. But I'm curious for views on these two different approaches.
Would you like to start?
Yeah, I can start. With respect to those, I think in a sense I agree on most of them. If you take a very liberal interpretation of deep learning, well, I can claim my system is also doing deep learning. Because at least multiple level of generalization that's absolutely necessary for any AGI. I don't think anyone can argue against that. Okay, that's one thing. Another thing is our system can also have the option of using deep learning system as a tool for some special purpose problem. That's also not anything I'm against. Okay, both of them I agree. But still, yesterday I gave the tutorial of my system. Whoever was here will know that that system is designed internally very different from deep learning. So in that sense, I will say, no, my system is not a deep learning system, even though, of course, you can find similarity here or there, and I can use it as a tool.
But you could build a pyramid of NARs, nodes, and links in the shape of a deep learning hierarchy, with the inferences, however, done by NARs rules and formulas, but the control would be determined by that hand-built hierarchy. That would be possible within NARs.
In principle, but I don't see the benefit.
Okay.
So far, I haven't been convinced about
All
the
right,
benefit.
all right.
I
That
would say
answers
yes, that's
my
possible.
question.
I think looking at these two possibilities, the first one's probably easier. You can take what you've got and you can put a system component in there that is a deep neural network. And that's nice in its own way. But I think the second one maybe hits the point a bit better because that's taking things as levels. I think there's a level disjointness here between the kind of concepts of the things you want to do in reasoning and so on, which is a little bit like GoFi, a bit like good old-fashioned artificial intelligence. And then trying to do them directly is one thing, but it may be very interesting indeed to try to do them using deep neural networks. So that means you've got a layered system with the kind of reasoning, etc., at one level, and then implementing these using deep neural networks. I think that's probably a different way forward, maybe a better way forward. Certainly a way forward in which you could use influences from neuroscience, etc., in as well.
I'm going to completely dodge the question and step back. It depends on what problem you're trying to solve. So
Human level AGI. As the initial step. After that, massively superhuman, super intelligent.
and that's still not a problem definition. So once you have a problem scoped out, then you can see how well your system.
Okay, take a robot college student, make a robot that can walk through at MIT and take all the classes and graduate doing the same things a human does.
Okay. Yeah, so you have a measure there. So my approach is to try both and see what works better. But I think your question raises a really important point, which is existing deep neural networks are really driven by what's easy to compute, more than what big task are we trying to solve. Like going from sigmoid functions to ReLU functions, they're faster to compute. And now the things that are fast to compute are being built in hardware by specialized card companies. And so those computations are becoming more and more ingrained in how we do things. And it is nice if that's what you want to do. Sometimes what I found is the actual problem I'm trying to solve is not well suited to the exact form of the existing neural network. And so it's useful to take perhaps the topology but take your own, say, OpenCog native structures and ways of thinking about it and use that as the substrate, the basic implementation.
I think, as I mentioned, deep neural networks are increasingly being designed in more complex manners, with the underlying architecture becoming more complex, and additionally, increasingly being used in hybrid systems. AlphaGo was an example of such a hybrid system, but we may see more complex hybrid systems in the future. But addressing Ben's comment, Leslie wrote a paper to accompany this panel that I encourage you to read, and in that he mentioned that we might view the brain as an instance of a deep neural network. And in that case, it contains a heterogeneous mix of functionalities And in the same way, we might add a third option to what Ben mentioned, where we construct such a heterogeneous mix of deep learning type networks. And I'm curious if, I remember you mentioning previously the possibility of implementing OpenCog in, for example, in TensorFlow, and you thought that maybe it wouldn't be feasible, but I'm curious if you have some thoughts about that.
I think TensorFlow itself is just made for running sort of one-off analysis jobs and piping results between them. If you looked at, for example, BRICA, B-R-I-C-A, which is a neural net framework made by the Japanese whole brain group, I mean, that's a sort of glue framework for connecting together neural net algorithms, which is intended for AGI, so the neural nets can be persistent and they can be temporal in various ways. So if you replace TensorFlow with BRICA, which is less well known but more AGI oriented, one could build some conglomeration of neural networks connected with BRICA that would be general intelligent. Now, whether that would be a network of deep neural networks in the current sense is a different thing, because if you're simulating like hippocampus with its spatial maps or the basal ganglia with its decision-making functionality, I mean, there are many parts of the brain that appear not to be architected in the way we currently would call it a deep neural network. So I would say if I was going to try to build an AGI using BRICA, it would have a bunch of different subnetworks connected together. Some of those subnetworks, especially those dealing with, for example, vision and audition, would have the architecture we currently think of as deep learning. The subnetworks dealing with decision making or spatial mapping probably wouldn't. Whether the subnetworks dealing with more abstract reasoning, like logic and language, would have that deep hierarchy as a primary characteristic, I don't know. My gut feel would be probably not, but that's sort of open research. Like olfaction wouldn't be. That, as Walter Freeman showed, is more sort of self-organizing asymmetric Hopfield net type architecture. So I think in the broader sense, that whole bricolage of neural net modules would be a deep learning system in the broader sense, because it's recognizing patterns and patterns among patterns and patterns among patterns among patterns, right? On the other hand, in the sense in which deep learning is currently used in the neural net and machine learning field, the whole thing would not really be a deep learning network. It would be a heterogeneous multi-neural net system, some components of which are deep networks as narrowly defined and other components of which would have different architectures.
We do end up, we're in some danger of ending up with a discussion of quite what's meant by a deep neural network.
Yeah.
And then it does get quite difficult. Other questions? Can we move on? Yes.
For all of you, when we think about humans specifically, or actually my own work tends to be in just subhuman mammals like deer or monkeys, it becomes clear that time is a gigantic constraint, as well as separating important signals from the unimportant signals. And I reify that to what everybody does, calls it attention. Right? And Cosmo mentioned in passing now that there's some work in deep learning in attention, but it strikes me that there needs to be more of that if deep learning is actually going to be able to be applicable in toto to anything like the AGI problem, specifically human or high-level mammalian processing in the real world. So I'd throw that out to the three of you and comment about the centrality or not of something like attention, and to what degree are deep learning networks likely to be good at attention.
I would like to start. Brandon?
So I'm going to qualify all of my comments by saying that everything I say is almost certainly wrong. We'll know the right answer when someone solves it. My best guess right now is that attention matters. In my own limited approach to it, it's the only way that I've figured out how to shrink the solution space small enough so you can do things like many step planning, and there's definitely biological precedent for it.
I think I completely agree with Brandon, and actually I will make it even stronger because according to my definition of intelligence, being able to deal with insufficient resource is a necessary condition, which means to be able to work in real time is absolutely necessary. So attention, as I just mentioned, should be in the structure in day one. It's not something you add into it later. So yes, actually that's one major reason I don't like the current deep learning, just because they ignore the time pressure. And one more thing, is more than what we usually call real time, because another thing about time pressure is it actually changes from situation to situation. You just say my system is very fast, so it's real time. No, that's not what I mean at all. It just for each concrete problem you have a time pressure that should be taken into account of your processing. That's what attention is.
Yeah, I also agree regarding its importance, and in recent successes in deep learning, a lot of it was in the field of supervised learning. However, I believe the field of unsupervised learning will increasingly need to see more progress. And when I talked about intrinsic motivation for unsupervised learning, that was some early examples of work in that direction.
I see time as being absolutely central here. Time is what allows an animal to live within its ecological niche. Time is absolutely central. And attention is a way in which an animal can focus on those aspects of the sensorium that actually are important to it. How you put time into either an AGI system which is built purely out of reasoning, or an AGI system that is built out of deep neural networks or whatever, it's not terribly clear at the moment. And that's partly because the kinds of problems we've been trying to solve have tended not to be those kinds of problems which are real world problems. Now they come up instantly the minute you try to do any kind of real robotics. So I think that's a really important area, and one that we haven't really got around to solving yet.
That's a leader question all the way.
Sorry?
There's a question.
There's a question all the way at the back.
Yeah, I have to admit that I'm a very shallow guy, so allow me to comment two things really shallow and try to ask a deep question. First of all, deep learning, deep neural network, is it just because it has a little bit more layers of network, we call it deep?
Initially, yes.
In my humble opinion, yeah, that's really shallow to begin with. But another comment is, actually, I'm more like applied guy. I come from system background, so I use a little bit of machine learning technologies to try to solve real world problems. So I think what deep learning really shines is, even it's so shallow, in my humble opinion, theoretical wise, it does solve a lot of problems. That's why people buy it. Whether I'm really stupid or not, I see it works. But on the other hand, the theory is really shallow. But okay, that's just my humble opinion. But on the other hand, it does not. It comes from bits, from pixels. But it actually, as you move up the layers of the network, you start to see objects, right? The problem is maybe with, like Ben's comments earlier, maybe with some heterogeneous architecture, we can start to understand context. That would be a big jump, right, to start to reason. Now, try to be a little bit deep here. My question is, I think so far we have been talking about the what and the why part. I think we're all clear. What is it? Why it doesn't work to a certain extent, right? But how about the how part? There's a bunch of smart folks here. I just wonder, toward AGI or human level AGI, how you guys think just a baby step toward that goal beyond what deep neural network can do right now? Well, what do you guys think in terms of how to lay out the plan?
Pei could talk about that for a few hundred hours.
Well, we are not supposed to talk about our own research in this workshop. We're supposed to talk about.
No, I'm sorry.
Yeah, I'm
sorry, Professor Wang. I really respect you, as you know. But the problem is that we all understand the what part and the why part. I'm pretty sure most of the guys here know what.
So to really solve this discussion is until you really have a better alternative, you cannot say deep learning is bad. Okay, you need to have a better solution to say we can do better. As Ben suggests, I do think we have a better solution, which I presented yesterday in the tutorial, and this evening we are going to have a demo to show our system how learning happens. And tomorrow I'm going to give a presentation about learning in my system. And but today I think we are supposed to limit to deep learning. So I will focus on why I think it's not solving all the problems. How to solve that problem? I agree. That's the final answer to this question. But probably we don't have all the time to discuss that in this workshop. So we can talk about it later.
So regarding that, do I think deep learning has a lot of hype surrounding it? Yes, I do. But I also believe that there is a rich body of work in the field that is applicable to AGI, and that's what I tried to give a slight flavor of in my presentation.
Your slide is very great, by the way. Thank you so much.
Thanks.
I think there's a sense in which you reckon deep learning was lacking a theory. That was something I picked up from what you said.
No, he said it was a shallow theory.
A shallow theory. I mean, there's a sense in which you can look at deep learning and the way in which these networks work as movement inside the phase space, inside a manifold, inside a state space of a really high dimension. And then you can start to apply physics tools to it as well. So I mean, it's deep learning as it is one way of implementing something which has got a huge amount of possibilities, and then you have ways of constraining movements inside that phase space and constraining what that particular sub-manifold inside the huge space is. There is a theory inside there. No, it's not the case that that theory is understood. But then, it's always been the case in science and engineering that the theory has tended to come a little bit later than the initial understanding of doing things. Theory doesn't, you don't tend to do the things based on the theory. The theory comes a little bit later. Okay. Yes.
Yes.
There's a microphone coming towards you.
How do you do grounding without DRM? And the corollary to that is how do you do multi-sensory integration with it? Brandon, you talked about that a little bit with the multi-sensory.
Yeah. So this is near and dear to my heart. My best guess, my intuition, I should say, about intelligence comes from evolution. You know, the cockroaches started doing what they did long before the rats started doing what they did, and biology is pretty good at repurposing and building. And so the grounding, I feel like, is like, well, if we get that right, it maybe makes the other steps work better. So I spent a lot of time thinking about this. And to be honest, you know, I think that's where deep neural networks shine. They can take these raw things and they make them into something useful. I just wish they made them into something more useful. To be able to say that this exact pattern of pixels might occur anywhere in the image, or maybe at a slightly different scale, or maybe with fuzzy edges or sharp edges. That's a good start, but it's nothing near as general as we would need to get to the symbolic representations that we were talking about yesterday. And I am going to play the we are not supposed to cite our own research in this forum and hold off on answering the rest of that. Although I'd love to talk with you later if you're still interested.
Sure. Others? Other comments?
I think, I mean, if you're talking about grounding, in a sense that's partly picking out information, which could be features, it could be symbols from that lower level, from the initial sensory data. And I wonder to what extent, you know, there's an issue which conflates, or maybe should conflate, features and symbols. Because when you talk about grounding, what do you mean? Are you trying to bring out particular aspects, or are you concerned about grounding in the sense of making sure that your deep neural network can react to its environment?
Well, I recall a book when I was teaching my preschooler how to read. And he would point to it and show the words, this is a picture of a ball, this is the word for ball. Then point to the picture, point to the word. How do they understand that? How can you do that? And that's more supervised learning
Not supervised learning, yes.
than unsupervised. But I think in the context of language, you need to have some supervision to try to put the context to these neural nets. Does that help?
I think in language that's certainly true. I think people don't independently learn language on their own. It doesn't happen.
Here's an example. Okay, are you familiar with this one?
Yeah. Magritte.
Yes. So, how do you train in an artificial intelligence the difference between the fact that this is a pipe or it's not a pipe?
I think that's trying to take a very fast run when it's just learning to crawl.
Wow.
It's an excellent question. That highlights the gap. That's, I think if we knew the answer to that, we'd be having a different conversation.
Okay. Behind you.
So, some of you may remember an article from Richard Feynman called Cargo Cult Science, and arguing that in certain fields people weren't paying attention to the literature in their own field and constantly reinventing their wheels or failing to reinvent their wheels and running around in square blocks. Do we find in the machine learning deep network literature that people have learned something fundamental, like here's the set of weights that make a good visual processor network, so then when you're going to learn to play Atari games, you've already got the visual processor part done? Or are we always reinventing the visual processor wheel every single time we do a deep learning, learn to do something?
I think there is a sense in which you're right, because people tend to put in the raw pixels as the input into the deep neural network. Whereas if you want to look at what we might learn, then we would have learned things like the various kinds of pre-processed features that people tend to put into actual visual systems, as opposed to putting into raw pixels. On the other hand, a lot of the time people are doing this work and trying to show that their particular system will learn these features well. I think if you were trying to use deep neural networks as visual systems, then yes, we're forgetting to read our own literature. But I think it's a question of what people are actually trying to prove there.
One thing that is actually really common is that more often than not, no one's trying to solve the general case. They're trying to solve a very specific task. You know, is this a cat or is this a dog? Or is this one of the set of ImageNet images, or is it something else? And so those very specific tasks often drive certain decisions and a certain approach that you wouldn't do the exact same thing trying to solve a different problem. And so that person is then has to start over from scratch or use a construct that's not well suited to their problem. So it's, I haven't seen anything yet that I would consider, you know, a nice, general, usable solution to that.
So I agree that this concept of transfer learning and incremental learning is a very important direction for research. And you mentioned specifically the learning of Atari games. In the original DQN paper, they retrained the network from scratch for each game. However, there was work presented at NIPS last year where they were able to transfer knowledge from one game's training and utilize it for further games in order to speed up learning. So I think it's an early thread of research, but there's certainly work being done on that.
Got a microphone?
So, Brandon, you mentioned the constraint of lower dimensional, I guess, information, and on this question of transferring and having a classification of, I guess, different sensory channels, for instance, what angle sounds more plausible to you guys? Having like several whole circuits of a DNN subsystem, each of which is working with a lower dimensional array, or trying to have like a kind of unified DNN system that manages to encode as if it had a higher dimensional array.
Are you talking about separating out different sensor modalities, like audio and video? Or are you talking about breaking it up into smaller groups or different types of processing?
Like I would say yes, audio and video is a great example, but then like audio and video has to extend to touch. And then, and Ben alluded to this yesterday, like a touch from the bottom of my hand feels different from a touch on the top of my fingers, you know? So like you can always separate into smaller and smaller down, is kind of the question. So like just audio and video, like yes, but also yes to the.
Yes, and yes.
About the processing.
Yes.
Yes.
And so again, I think we'll know the answer when someone builds it and it works. My gut feel though is that if I have to custom design my network to the exact collection of sensors that I have, then it's not a general solution. So whatever I do should be able to take, maybe I take physical sensors out of it altogether and I start feeding in stock prices and economic indicators, and my actions are buy, sell, trade, and I have a clear reward signal there. That I should be able to learn that too, is my intuition. It shouldn't be dependent on knowing what the information means before I get it. Most of the time we're solving we being people who are actually paying to have these problems solved, they're solving problems that are much narrower than this, so they have to deal with this. But I think in order to call it AGI, we have to be agnostic as to where it comes from.
I think that trying to solve the whole problem all at once is almost doomed to failure. Because then what you're doing is you're saying, I have this really, really clever system which will do all the processing that I need. And I think that really you have to expect to pick up aspects, features, symbols, etc. from some of these inputs. Also, I'd suggest that when you come to look at transference, the ability to break down the problem and to solve it piecewise means you can transfer things that you learned early on, lower level things, to solving different problems. So if I want to recognize cats from dogs from mice, then I'm going to pick out certain aspects. Then my system will probably pick out certain aspects of the visual feature space. And that sort of visual knowledge is also going to be useful in solving problems like finding a door or looking at a moving set of images. So I can remember 30 years ago people talking about neural networks and saying, yes, we'll just put the raw data into it, we'll just point the camera out of the window and the neural network will solve this problem. Right? It didn't happen then and it won't happen now.
Also, the integration, does that happen inside the so-called deep, or does that happen at the output?
I think it happens inside. If it happens at the output, just at the output, then I think you're still trying to solve the problem all at once.
Yeah.
I mean, if you go back to teaching children reading, you're relying on their visual system having picked up ages, etc. Now, some of that's inbuilt, okay, some of that's actually been found by the genetics, but some of that is being trained up by the child's eyes and so forth, by the child's eyes and visual system, really very early on, pre-birth and at birth, etc. So I think that these kinds of early trainings, picking out certain kinds of features, certain kinds of, I'd like to call them symbols, but I'm not sure if that's the right term to use, actually can happen inside the system in a self-organized way, and you're then going to reuse that in more sophisticated and more difficult and more complex problems that you have to solve later. Somewhere over there.
When we are talking about the gap between AGI and DNNs, we frequently make reference to human-level intelligence. We also talk about human brain when we are talking about neural networks and things like that. But when you look at the nature, obviously, all different forms of animals and also vegetables and microbes, they have different forms of intelligence. So, from that perspective, and probably humans are, when we look at right now, humans exhibit maybe the highest level of intelligence, but certainly there will be other forms of organisms maybe in the future who will exhibit higher levels of intelligence. So from that perspective, do you think it is a good idea to look at, to bring human level intelligence into this discussion, or is it a misplaced focus?
So I have a strong feeling about this, so I'll voice it really quick. Intelligence is poorly defined enough. I think most of the time the term distracts us. I strongly encourage anyone doing work in this area to be really crisp about what it is they're trying to do. So as crisp as I've been able to be, is like my lifelong and probably further than that goal is to build something that can do everything that I can do, whatever that is. But that's very different. Some people want to understand how the human brain works. That's not my goal. And some people want to create something that will reason rationally by some definition, even in very unfamiliar and non-physical environments. That's also not my goal. But what is helpful is when people get very specific about what it is they like to do, and then it helps a lot of conversations that go in circles to go away.
Extending on that, regarding defining what we're trying to do, Ben has written several things on defining general intelligence and efficient general intelligence, which are useful. Additionally, Marcus Hooter and Shane Legg wrote an entire review paper on definitions and measures of machine intelligence, which I would encourage you to look at if you haven't already seen it.
Back at the AGI conference in 2008, I put in a paper saying that we should be looking at artificial general intelligence in some really simple organisms, and I singled out the paramecium, which is a single-celled organism which clearly hasn't got a nervous system of its own, and yet it has sophisticated and complex behaviour. So in that sense, I'm very much in agreement with you that we need to look at other sorts of meaningful intelligence as well. It's true that in terms of large animals, humans are the dominant species, although in terms of single-celled animals, there are probably other animals with larger populations, though the total biomass of those animals is rather less. But if you start looking at how really simple animals, like single-celled animals, behave in their particular ecologies, you soon realize that they appear to be exhibiting certain kinds of, certainly task-orientated and possibly intelligent, but it's hard to define what you mean by that, behavior as well. And I think that we should be looking at that as well. So yes, there's an issue there. The gap that we're looking at between AGI and say the DNNs isn't just a gap of implementing the one in terms of the other. There's something deeper in there as well. If you start thinking of intelligence as embodied in animals, there's something else there too.
How does that tie in with the distinction of sort of an agent versus a tool, do you think?
Well, I think a paramecium is an agent rather than a tool. So in that sense, I'm not quite sure what a tool would be in that sense. Perhaps the flagella of a paramecium is a tool, but the paramecium itself certainly appears to be an agent.
Yeah, I also happen to have a very strong feeling about this question. It's so strong. Actually, my very first paper published in the very first AGI conference is titled, "What do you mean by AI?" I still see it until today. As Brandon said, actually we are not really working on the same problem. We're working on a bunch of related problems. We need to be clear about that. At this moment, there's no way for us to convince each other what is the true or correct definition of AI. But we need to make our own goal clear. So this is what I want to do. This is what you want to do. What we can learn from each other. In my first paper, basically my argument is, yes, there are more than one goal. Yes, they're all valid for science. But no, they're not the same goal. We need to be clear about both sides of this issue.
Over there. Plenty of choice.
I have a quick question. So the brain, like the human brain, clearly is like an end-to-end system that implements.
It's not switched on, just press the button.
Hello?
Yes.
So clearly the brain is kind of an end-to-end system that implements multiple cognitive algorithms that taken together exhibit what we think of as general intelligence. But it does this using the deep networks that we're talking about. I guess my question is, correct me if I'm wrong, but any kind of classical software engineering problem can be represented with this networked approach, with weights and vastly parallel inputs. But clearly, some things can be done using classical approaches, with a standard, von Neumann computer, memory. And, is there a fundamental benefit to approaching those types of problems in an end-to-end deep network fashion versus plugging in the deep learning where it makes sense into a broader system that also includes classical approach?
Yeah. If I could restate your question, is there anything magic about deep learning? Is that what you're getting at? Is there anything that is absolutely special that means it
No,
needs to
I
be
mean,
included?
is there a benefit to looking at the cognitive algorithms from the deep learning perspective versus using what's easier to us to implement certain algorithms and then plugging in the more perception problems in where it makes sense?
So like, is it worth trying to use deep learning for everything rather than just where you can?
Yeah.
Sort of universal.
Probably not. But on the other hand, trying to write software to do recognition problems is extremely hard. So, yes, my usual answer to that is, if you can write the algorithm down in a nice, straightforward way, then write a program to solve it. But if you can't write the algorithm down, then maybe you need the help of some kind of system that does generalization, like deep neural networks, etc.
I like Gary Marcus's analogy of it's a screwdriver, and yeah, you use your hammers and your wrenches when it's most appropriate, the right tool for the right job. If you're predisposed to using your screwdriver for everything, you probably won't do as good work. It's like every analogy, deeply flawed, but it's my approach to it.
I actually also use that analogy from time to time. To me, traditional AI or computer science, they're building tools. To me, AGI is building hands. The difference, again, is related to some previous discussion. That is, for any given special problem, usually hands are not the best choice. Special purpose systems almost always work better if you're only interested in one problem. But the hands give you the benefit of flexibility and so on. We know they are not going to treat this with any tool. And that's what I mean by general purpose. It doesn't necessarily mean to do the best any special domain than any special tool. It is actually the other way around.
Have another question? Simon?
How do you see deep learning developing rich internal models?
Can you elaborate on what you mean by rich internal modeling?
Internal self or world models, models of things when doing some tasks.
I would say that the research fields of deep generative models and programming learning are both relevant to that.
They're relevant, yeah.
I actually think that's probably the most critical question. If we're talking about deep learning and deep neural networks, etc., is how are they going to generate internal elements, internal models? Because that's where transference is going to come from. If each problem has to be solved independently of every other problem, then that's a really difficult situation that we're going to be in. If on the other hand, you can make deep neural networks learn independent tasks, independent subtasks, then that's reusable for later tasks. So I think that is a really important question. I think it was referred to in some of the papers that were in your talk, in your presentation. Question up, far back.
Far back corner.
Far back. Way over there. Seems unfair to... I'll come back to you next. Way in the top right. Top left, sorry.
Please talk to the talk near to the microphone because otherwise
I want to go back to the hardware metaphor and to ask, aren't we kind of holding a hammer and treating everything like a nail now? Because I kind of feel that this is maybe the current situation with neural networks since they became so popular in a way and almost easy to use. We have this endless amount of packages and NVIDIA are giving free GPUs, so let's just write something that runs on a GPU. And I think Brandon, you mentioned it, that we have this like designated hardware now, that if we can compute rather faster, so let's use it. So my question is, how do we make sure that we're not, I don't know, hammering a cat by accident?
There's definitely, another metaphor is the erosion. Like the more people walk the path, the deeper it gets worn and the more people will tend to walk it. My other hardware metaphor for deep neural networks is a rocket engine. If you know right where you want to go, you can strap it on your bicycle and aim it in the right direction, and it will get you there really fast. But there's no inherent virtue in incorporating a rocket engine into your design if you don't know exactly what your destination is. And the application of that is, deep neural networks can do some amazing stuff, but if the way in which you're using it, or the algorithms that you use to incorporate it aren't exactly what you need to solve the problem, you can't just hope that faster is better. And I've heard that stated explicitly as a justification for using deep neural networks. So like anything, there's huge danger of falling in love with our tools, particularly academic incentives seem to lean toward, hey, I've got a tool, I'm going to make small changes to it and publish on it again and again and again, instead of clearing new ground and starting with something else.
Just see one more thing. The world is littered with pieces of hardware that people put together. There's an Intel 8870NX chip that came out in 1993 or so, which was going to be the neural network chip. It didn't work out.
So I have just one comment, just regardless of how applicable deep learning is to AGI, I guess at least it's bringing credibility to the space and it's achieving some particular capabilities, and so it's bringing credibility to space. People aren't just hard coding features, or so. At least it's moving us more towards attention and focus and funding on AGI anyway. But I guess one of my thoughts, and I don't know if I can quite frame it in a question yet, but human beings are not there's not just one person. We are actually like it's that we're able to be organized societies, that we have culture, that we, if there was just one human being and they lived for 60 years, that would have been not, that would have been kind of the end, obviously. I mean, there was that example of the baby ibex that, right out of the womb is able to, navigate its way down a cliff face, but for human beings, clearly it's a lot more than that. And one of my impressions with the deep neural network stuff is it's not the paradigm isn't based on the idea of multiple agents that are able to learn and then share knowledge and then expand from that. And then the other part is that so much of AI and computer science is still based on the idea of this single algorithm that has its closed world of variables and only makes sense in the context of the algorithm from when it starts until when it ends, which is, very heavily influenced by the mathematician's paradigm, I guess, for lack of a better word. And we need systems that can understand an algorithm, can understand multiple algorithms, can reflect upon them, can choose between them, can work outside of the algorithm. An algorithm that can understand an algorithm. I don't know if I'm being very clear on that.
Better algorithm. Hi, that sounds like you.
Yeah, I would say I fully agree with the comment. And also I see that as a key difference between special purpose system and the general purpose system. A general purpose system, once again, is not a collection of special purpose systems. To me, it's a different task or a different problem by itself. So today, I see, again, for deep learning, I think the value of this workshop is not to say whether it's good or it's bad. Clearly, it's good. But just like every technology, it has its capability, it has its limitation. Now in the public discussion, very often people are not paying enough attention, or the limitation is not very clear. That's what I think this workshop can clarify. What it can do, what it cannot do, for what reason. We want to make that clear, so we will know that in the future, in what situation we can depend on deep learning. So actually for AGI, I think the difference is deep learning to a large extent is still targeting on one task. Each time targeting, well, of course it can target on different tasks, but each time is targeting on one task. But intelligence for me in general have to be able to handle multiple tasks at the same moment, balance against each other, even though they're maybe probably not directly related to each other. That is something I don't think deep learning is contributing at the moment.
I think I agree with Pi. Deep learning is not contributing in this sort of way just now. Part of that is the way in which research gets done. I mean, each person has got to do their piece of research and write it up and so forth. So in a sense, there's a sort of cultural view which says, well, you have to write your deep learning algorithm and deep learning system and make it go and then write it up, and then you get your paper or whatever out of it. Trying to make systems work together inside a culture is what you're also talking about. In a way, there was a bit of work done on that with swarms of robots. But in order to make a deep learning system work inside a full environment, I think you would need to have a number of them embodied and actually going around inside the world, doing something, maybe talking to each other. I think we're quite a long way away from that just now. Other questions?
Yeah, I was wondering, going back to a response you had to a previous question about if we're building an actual general solution to AGI, that we need to be as agnostic as possible. And I was just wondering, just how agnostic do you really think we could be, considering that, our best example of a general intelligence is ourselves. And as Ben was maybe talking about yesterday, that we developed kind of, through nature, kind of in synergy, all these different components. They kind of had the benefit of growing together, and then we ended up as these intelligent agents. And then I guess us in the search for AGI, we're kind of taking a shortcut. We don't necessarily have that benefit of these things growing together. So at some level, don't you think there will have to be some context dependent or assumptions that we make that prevent us from being purely agnostic about the approach to general intelligence? And I guess, do we have a line, or are we figuring out a line that starts?
Yeah. Let me jump in, since I made the earlier comment. So either extreme, I think, is problematic. Solving point problems that might have monetary value to a company, not AGI. My very crude understanding of the no free lunch theorem is that if this is the solution of problems you want to solve, you can only do so well across the board. The only way you can improve on everything is by reducing that scope a little bit. If you want to solve all possible problems, then you'll do most of them very, very poorly. But if you want to restrict it a little bit to say like physical environments where gravity is 9.8 meters per second and time proceeds forward, and a few other small assumptions, you can increase that quite a bit. And so it comes back to defining the problem that you're trying to solve. If you broaden that out, you automatically bring your ceiling down a little bit. And if you make it too narrow, that ceiling goes way up, but then you lose the benefit of interestingness, at least in this context. So as long as you're very clear about what you want to do, it's okay to, in my opinion, to draw those lines there. My comment was motivated by the fact that I'm assuming that, say, again, my perspective, I want something that can operate in the physical world like a human adult does. If I have to go in and engineer every part of that, well, as long as it does well on all tasks, I suppose that's acceptable, but that's theoretically not aesthetically pleasing.
Is Tom Everett here in the audience?
Another question? Right in front of you.
So further to your point of narrowing the field of intelligence to things working in this world, or with these specific features, wouldn't the question of true intelligence be able to operate in different worlds without fundamentally being changed? The aspect of intelligence that we're after would be that type of problem solving that should span or should join all those different worlds.
I'd like to redirect that question to Ben.
Infinitely general. Yeah, I mean that really gets back. I mean, you cited the no free lunch theorem. There's a lot of different ways to slice it mathematically, but I mean, given infinite computing resources, in theory, you can make a system that can handle any computable goal function, any computable environment, which ties in with Marcus Hutter's AXE work and Schmidt-Huber's Gödel machine and so forth. And then when you restrict scope to some finite amount of computational power in terms of space and time resources, you're intrinsically going to somehow restrict the scope of problems that your system can deal with. So I mean, if you have restricted space and time resources, you're not going to have ultimate unbounded general intelligence within those constraints, and then it sort of comes down to, within the constraints that we care about, which could include, say, we have like 3 dimensions of space and one dimension of time, or it could be other subtler restrictions. Within those restrictions that you care about, how much generality can you get within a certain amount of resources? And then, of course, then it gets quite subtle because your system can glom new resources onto itself. It can build new processors and shove it into its head, but there's limits to how fast it can do that given special relativity and so forth. But I mean, in practice, if you look at space and time resource restrictions, humans are not arbitrarily general intelligences. Like we can't prove arbitrarily complex theorems within our lifetimes. Like we can't navigate in 98 million dimensional space in a tractable way in reality. And you sort of go into mathematical la-la land there, which sort of brings you back to his point that like right now we can think about making something that can do everything that humans do. They can graduate college, they can prove more theorems and do more science than us. And once we've made something that's maybe 10 times as smart as human beings in this 3 dimensions of space, 1 dimension of time, maybe that modestly, superhumanly intelligent AGI guy will obsolete all of our theories of the AXEans and then computing and intelligence anyway. So maybe that's far enough ahead for us to worry about thinking. Right? Pei has something else to say.
Add a few words. In my opinion, when I say my system is general purpose, that means when I design the system, I'm not assuming it's going to solve any specific problem. But as soon as you build that as general purpose, the general purpose is basically a potential. Okay, when you begin to train it in a certain domain, it will of course become special purpose for that domain. It's just like us. We are not really expert in every domain. Okay, you are bounded by your education, and your education basically lead you to a special domain, so you perform better than in the other domain. In that sense, yes, we are going to become narrowed down, but of course still quite flexible or general in today's computer. But I'm not talking about even after that training, you are still general purpose in all fields, which I agree with Brandon. There's no way for you to be an expert in all the fields to the same level of expertise.
Okay. One more question from that? I'm sorry,
I was just
your
stretching
question. I was going to say one more thing to that, which is that a few years ago I went to the Edinburgh Festival and somebody had put together a bicycle where when you turned the handlebars that way, the wheel went the other way. And they were offering a fair large sum of money if you could bicycle more than 5 yards on it.
What if you sit backwards?
I saw people try all sorts of things. I didn't see the man lose any of his money at all. So we're general purpose, but we're not all purpose. One more question?
Yeah, to kind of follow up on what you just said, you know, humans are general purpose in a certain sense, but the most intelligent human has never learned how to speak with a cat, for example, even though cats quite a bit simpler than us can figure it out, well, if that's speech. So when we talk about these general problems, or general artificial intelligence that can really tackle any kind of problem, does that really exist, or are we always going to be like very profoundly limited in the scope of problems?
I don't think we know the answer to that.
I guess to be more specific, what I'm really asking is that, Brandon earlier said that we have to, you don't have to hand choose the functions to design a human that can work in our world and perform the way we can. But evolution has done that for us over billions of years. So is that really a realistic expectation to have a system that can perform like a human without that amount of training to specifically do that?
That's an excellent question, and I think we'll know when someone gets working.
Well, that's a different question, because an AGI can have a quite different kind of training than evolution gave it, because the AGI can have sensors all over the planet and can, in theory, could read stuff from everyone's phone and every surveillance camera and read the entire internet. So it has a lot of data over a narrower slice of time, which is different than the information that went into evolution. So I mean, that doesn't answer the question, but it does mean like it's not like AGI has a small subset of the data that evolution had. It's just in a way a different sort of situation.
The question of how much hand engineering will be required, though, I think is an open question, and a big one.
And also the definition of hand engineering is very unclear. I mean, as deep learning raises, to what extent is providing labeled training data hand engineering, or when you're running an unsupervised learning system, what data do you provide to that unsupervised learning system? It's not supervision, but it's guiding it to look at some things. So there's
You may not be adjusting weights, but you're manually doing the art with the hyperparameters.
Yeah, but on the other hand, even if you don't do that, I mean, you're pointing it at some cameras and not others. I mean, and you're building the thing, right? So, I mean, what knowledge do you put in when designing the software? So, I mean, where you draw the lines between hand engineering and not between code and content is just, it's not very, very clearly formalized. In the end, we're infusing a lot of knowledge into the architectures. I mean, say in OpenCog, we have a 3D time-space map. Like, okay, that's not cognitive content. It's part of the C++ code, but I mean, we're putting that in there because we think space and time are important enough to merit being part of the plumbing, right? So we are infusing it with a lot of knowledge in a whole hodgepodge of different ways. Right?
I think it's an extremely interesting question, and it also came up yesterday in a slightly different context of reference machine design in the field of universal induction. And I don't know to what extent we need to pre-design our architectures, to what complexity, and to what extent they should be expected to learn from a simpler architecture, but I think it's a very interesting question.
One last question. I'm conscious that it's after 12:30.
Hi. So historically, deep learning has been sourcing the human brain for its inspiration from things like visual cortex for convolutional neural networks to systems like hierarchical temporal memory, which tries to emulate the cortex quite close. Is there a reason why deep learning community is kind of focusing on one part of the brain and then ignoring that the connectivity requires like thalamic loops, and it's a lot more complicated? And I guess the broader question would be: is anyone working on the problem of architecture, where you would actually take all those different algorithms and develop new algorithms to actually solve AGI with deep learning?
I'm going to start off by answering the first of your questions. I think the reason why people have gone for the cortex is that the cortex is particularly human, in as much as humans have a particularly large cortex. But that ignores cerebellum, brainstem, the midbrain, and so forth. And I think I quite agree with you, but that isn't really appropriate.
It's also on the outside, so it's the easiest thing to get to, so that's why we study it the most. But it's been around the most recently evolutionarily. But deep neural networks do not resemble the cortex at all. They are only, in the most superficial sense, cortical. Gary Marcus made this point earlier, and if you actually look at the connectivity and what they do, we have no idea, in the sense that you can find papers that describe many, many, many connections and many different possible functions. So what this lets you do is start with a hypothesized cortical function, and you can essentially overlay that over cortical structures and find a plausible mechanism for implementing your theory, no matter what it is. It's like having, you can go out in the night sky and look at the stars, and you can find the collection of stars that show the shape that you want to show. And our knowledge of neuroscience is that sparse that we can do that. This is my personal opinion, of course. I believe that there are efforts to do what you talked about and find the algorithms for all these different pieces, but it's just so big, it's so hard to wrap minds around, it's so hard to get consensus on, that the most we have is a number of small proposals for small pieces and small networks that we understand well.
Whilst it may be true that deep neural networks aren't very like the cortex, they're even less like the brainstem or the midbrain.
Yeah.
We have a little more connection perhaps to the cerebellum, perhaps a little bit more similarity. There are people who are trying to put together different areas of the brain in different kinds of systems, but they're rarely getting together with the deep neural network people, so they're rarely putting together the systems made up of both different parts of the brain and these kinds of deep neural network simulations.
One example of that is one of the papers I cited from Diane about the hippocampus and the model-free episodic control deep neural network that takes inspiration from that.
Well, I'm conscious, I don't know how long I'm allowed to go on for, I'm conscious we started 10 minutes later.
This is probably a good time to end.
So can I thank everybody very much for the questions? Can I thank the speakers for their talks, and can I thank the
Thanks to you for organizing this as well.
We'd like to thank our
Great
conscripted
workshop.
microphone runner as well.
Yeah, if you tell me how to get to that drive, I'll be more ready. So this is on this computer, and then it's no name. Does that sound familiar?
Well, my gut feeling is that there will
So I just plugged it back in.
There, let's see if.
Oh, great.
Thanks for the feedback.
Recognize it being
Do you know what he's doing? Like your question. Thank you. What do you? I'm not working.
You can make an 8. If you want to, neither am I.
Okay.
But it's gonna make a difference.
Where are you based? Very nice. Oh, okay, Juniper, yeah. That was no name.
That was no name.
So we, so anyways, I have nothing to do with my work, with my work. Oh, you know what? I was, when I was in grad school, I dismissed AI as a subject years ago, and then 2 years ago I read the.
Just on this computer.
Okay, it was on this computer.
Okay, so I just
On the
wanted
work in
to
progress.
Turned back onto the subject. AGI was, the text
Okay, there's the Seagate.
brought it together into cohesive theory. What I used to think was just a bag of tricks. Thank you very much. Okay, so here's done a good job. Anyway, so I got back into it, and I'm just attending a few conferences, once every quarter.
Yeah, I was just trying to be helpful with.
Nowadays, I'm a closet.
That's it. Okay, I'll go.
Half of the sales force in the city. So I'm a sales guy.
Yeah, kinda.
There